Alrighty, howdy folks. Let's switch backwards. In fact, we are going from chapter 6 to chapter 5. This is what I was trying to tell you. So I know that this order is a better order than what the book has, okay? So that's my judgment of it. So please bear with me on that. Okay, this is about trigonometric graphs. And what that is, um, let me talk about this in a second. What it is, what did we do so far? We learned how to find the trig function values, trig ratios at different angles, right? For example, 0 degrees, 30, 45, 60, 90, and then keep adding like 0, 30 to all of that, which means 120, 135, and so on. But what about in between angles? Something like 36.5, 28.94326. Are there trig ratios for that? Yeah. These trig ratios are actually, they can be computed for any angle, as a matter of fact. Cool. So what that leads us to is trigonometric functions. So we are no longer dealing with simple trigonometric ratios, but each one now becomes a function because each one of those ratios can be computed at just about every value of the argument. I'm going to use that word argument. What that means is when we say sine of 45 degrees, that 45 degrees is the argument. So for any value of the argument, we can actually find the trig ratios. And that automatically leads us to trigonometric functions. And that's what we are trying to do now. Okay. Since we want to learn about the graphs of trigonometric functions, my suggestion is there is a free software called GeoGebra. Okay. And I particularly like the Classic 5 edition. Probably I could learn the other ones, other newer editions, but somehow I stick to something that I know. Okay. And the beauty of this software is we can easily draw graphs. Okay. For instance, maybe I will actually go ahead and show you that. How should I do it? Yeah, maybe I'm in a dilemma how to proceed. Okay, good. Let's say when you open the GeoGebra Classic 5 edition, it looks something like this. All right. And there is this input box here. In the input box, if I simply type f of x is equal to x cube, x, you have to draw the caret, x cube plus x square plus 1, something like that. Boom, and hit return, hit enter. We got the graph of that function. And I have now clicking my left mouse. Clicking the, what do we call this, left click. I'm doing a left click on my mouse and dragging it. It allows me to drag this. And if I do a scroll on the mouse, I can zoom in. So a scroll up is zooming in, scroll down is zooming. Did I say that right? Yeah, scrolling down is zooming out. So you get to see more of it, whereas if you zoom in, you can see a small portion, but in greater detail. Okay, that's the idea. It's as simple as that. Look at how simple it is to draw a graph. If I want another function, let me call it f1 of x. The previous one was f of x. What if we didn't want to draw the graph for the whole domain that it is defined? Instead, we want to draw it only, say, from -1 to 1. What graph How about x square? A simple x square drawn only from -1 to 1. So how do we accomplish that? Using this. We'll say f1 of x is equal to function function, and we want x square graph, right? So first indicate what that function is. X caret 2, that means x square, comma, -1, comma 1, right? All we wanted it was to be defined in the domain of -1 to 1. So the -1, comma 1 accomplished that. If I hit enter, ta-da, there's our graph. Cool. So drawing graphs is so much simpler using GeoGebra. And then we can actually do a whole bunch of other interesting things using this GeoGebra. And I'll show you all of that stuff. Cool. So let me get back to my PowerPoint. What did I say here? Let's quickly go. For instance, to draw the graph of y equals x squared plus 1 in the input box, this is what I showed you, right? Type f1 of x is equal to x squared plus 1 and hit enter. Voila. You see this graph. And I also talked about what if you wanted to draw a graph only in over a certain interval. Then you can do y equals, if you wanted this, you type f2 of x is equal to function x cube minus 1. That defines the function. And then you say -1, comma 1. So that defines the bounds of your x. And as a result, we get this graph, right? Cool. Now, what was the whole idea? The idea was, hey, how about the graph of sine x? Okay. And to do that, I want to show you something else first. I want to show you something really cool using GeoGebra. Check this out. What do I have here? I have a circle whose radius is 1 unit, and I have a point P located here. And basically, I can increase theta. This is what is called a slider. So I created a slider using this thing, and I have created a slider for theta, and I'm changing it from 0 to 2 pi. Okay, I'm giving you so many details right now. Let me run this and then talk about all the details. So if I have this theta, I can run that. I can say animation on by right clicking, and theta increases, and as a result P changes because P has been defined like that. Okay, so basically P is dependent on theta, and so as you can see, this is just P is just moving around a circle. Cool. Okay, now what's the point here? The point I'm trying to drive home here is, now suppose I keep track of another point Q. Q is simply the y value of P. Let me repeat that. What is that Q that you're seeing? Its x value is not changing, but its y value is changing, and it is in fact equal to the y value of P. So far as P is concerned, both x and y values are changing as it rotates along the circle. Whereas Q, the x does not change, y changes exactly as the y value of P changes. So notice how this is moving up and down, right? Q. Now I'm going to do something else. I'm going to keep track of another point called S. What is S? S looks like this. Okay, what is this S then? The S is doing something like this. Let me pause it for a second and try to explain what S is. S is basically the same Y value as P, but its X value is this theta. Let me repeat that. This point S that we are seeing here has the same Y value as P, but its X value is this theta. Over here, theta is 0, and therefore this X value is also 0. As I move this to here, that is about pi over 2, and 1.57 is pi over 2, and X value is pi over 2. Right? So that is the kind of curve that is generated by a point moving along a circle. And ladies and gentlemen, this graph is the graph of sine x. So sine is called sine and cosine are called circular functions because the y values of a point that is moving along a circle behaves like a sine curve, and the x values behave like a cosine curve, and that's why they are called circular functions. Cool. So this is the motivation for learning about this, about circular motion and sine curves. Now, what should I? There's something else. So you might be wondering, hey, come on, man. I'm not so sure that all these things are the same y value. Well, suppose I were to put a line there, okay, a horizontal line. Now, would you agree that all P, Q, and S are the same y value? Now, if I run the animation, you will see continuously P, Q, and S happen to fall on the exact same horizontal line. So they all have the same y value. Okay. So this is what a sine graph looks like. And what I have done is just taken this theta to go from 0 to 2 pi and back to 0 to 2 pi. That's why it's coming back like this. Did I keep increasing it or let me see. Yeah, 0 to 2 pi jumps back to 0 and again goes to 2 pi. That's the way I set this up. Okay. But the truth is, I could let the theta go from 0 to keep on increasing it. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, keep on increasing like that. In that case, the sine curve would keep on going. And in fact, when we do something like that, the actual sine graph looks like this. There is no end to this. It just keeps going and going and going and going. Okay, so this is the graph of sine x. Take a good look at it and be absolutely sure to understand exactly all the characteristics of this sine graph. Cool. First thing, when x is 0, is sine x going to be 0? Is the y value 0? Is that true? Well, all you need to do is ask yourself, is sine 0 0? Yeah, sine 0 is 0. That's what we learned. Okay, what else? What is sine of 90 degrees or sine of pi half radian? Isn't that equal to 1? So when x is pi half, sine pi half should be 1. Shouldn't this be the point on the graph of sine x? Yep, look at this. The y value is 1. And again, what else? Sine of pi, sine of 180 degrees, that is 0, right? And sure enough, we have at x equals pi, we have sine of x to be equal to 0. The y value is 0. Sine of 3 pi half is negative 1. Sine of 2 pi is back to sine of 0, and that's going to be 0. So we have completed one full circle by the time we let x go from 0 to 2 pi. Cool? If you need to pause the video, please do that, and be sure to grasp all those things, all those concepts. What is certainly important, maybe I'll point out this. We know about the quadrant system, right? First quadrant. What is first quadrant? When theta lies between 0 and 90 degrees, or 0 to pi half. In the first quadrant is sign positive. In 0 to pi half is sign positive. Yep, it is. Now, would you agree that all these y values from x equals 0 to x equals pi half happen to be positive? Yes. Are they increasing? Is it true that the sign values increase as we go from 0 to pi halves? Yeah, sine 0 is 0. Sine of pi sixths or 30 degrees is 1 half. 45 degrees is square root of 2 over 2. Then square root of 3 over 2 at 60. And finally 1 at 90. Right? And sure enough, those values are increasing, and the graph clearly indicates that the values are increasing. Right? Okay. Now, after pi half, between pi half and pi, we are in the second quadrant. Is sign positive in the second quadrant, pi half to pi? Yeah. All student sign, it's positive. And is the graph indicating that the y values are positive in that interval? Yes, it is. So this is correct. And then what happens? When we go beyond pi, between pi and 3 pi halves, we are in the third quadrant where sign is negative, and sure enough, all these y values are negative. And from 3 pi half to 2 pi, we are in fourth quadrant where sign continues to be negative, but the values are increasing. And then the moment we come to 2 pi, we have done a full circle and we are back to being 0. And then the behavior is exactly the same as what was here. The behavior after 2 pi is exactly the same as the behavior after 0. Right? So, so this actually makes sense. Somebody claims that this is the graph of sine. We can say, yep, I see what you mean by that. It is, right? So this is the graph of sine. Are we clear? You must be able to draw the graph of sine. When you do, what are all the things that you need to show? The important things, which are what? That at x equal to 0, sine x is 0. And the shape of the curve is like this. And at x equals pi half, the sine graph reaches a maximum value of 1. At x equals 3 pi halves, it reaches a minimum value of -1, the smallest value. Then heads back and becomes 0 at x equals 2 pi. You got to be able to show all these x and y values fairly accurately. And then keep repeating the same pattern, both to the right and to the left. Cool? Are you clear about how to draw the sine graph? All right. Once we do that, there is something else that we need to look at. I've talked about all of that. Okay. Periodic function. There's something called periodic function that we need to become aware of. So the definition of a periodic function is a function f is called periodic with a period p if f of t plus p is equal to f of t for every t. What? We call a function f as being periodic if it so happens that f of t plus p is equal to f of t for every t. Or I could have said f of x plus p is equal to f of x for every x. The question is, does the sign look like a periodic function? Right? Let's see. Let's look at x equals pi half. At x equals pi half, sine of x is what? 1. At x equals pi halves. Suppose I add 2 pi to pi halves. 2 pi plus pi half. Can you do that? 2 pi plus pi halves is 5 pi halves. Right? Okay. At 5 pi halves, does the sine have the exact same value as it did at x equals pi halves? Yep, it did. So, could we say that sine of pi half, or rather sine of pi half plus 2 pi is exactly the same as sine of pi half? Let me repeat that. Could we say that sine of pi half plus 2 pi is the same as sine of pi halves? Isn't that looking like f of t plus p is equal to f of t sine of pi half plus 2 pi equals sine of pi halves? And it's not just that. I could have picked sine of 0. So make the t to be 0 and p to be 2 pi, and then sine of 0 plus 2 pi. Is that equal to sine of 0? Yeah, when sine of 0 plus 2 pi is sine of 2 pi. And sine of 2 pi is also 0, just as sine of 0 is 0. Right? So we can keep on doing that stuff. At sine of 3 pi halves, sine of 3 pi halves is -1. Add a 2 pi to it, you get 7 pi halves. And sure enough, sine of 7 pi half is also -1, just like sine of 3 pi halves. Right? Any other intermediate value for t that we pick, it will turn out that sine of that particular t plus 2 pi will be equal to sine of t. And so sine is in fact a periodic function. And we say, is the sine function periodic? Yes. If yes, what is its period? Well, sine is periodic and its period is 2 pi. And that is sine of t plus 2 pi is sine t. Another very important concept. Cool? All right. Well, what's the next thing that we need to learn? If you recall, there's something called linear transformation of graphs that we learned. So that means your teachers will say, hey, let's try to find out how to draw the graph of f of x equals x square or y equals x square. Right? When they do that, they show you that it is a parabola. And then they say, if you know the graph of y equals x square, do you know how the graph of y equals 2x square looks like? Y equals 3x square looks like? Or how about y equals x square plus 1? How about y equals x square minus 1? So all kinds of combinations they look at and they say, do you know how the graph of that would look? Which is all nothing but linear transformation. In general, the concept is, please pay attention to this. In general, the concept is knowing the graph of y equals f of x. Could we figure out how the graph of y equals a times f of bx plus c plus d look like? Here, my f happens to be sine, so that's exactly what I'm talking about. We learned how the graph of y equals sine x looks like. Now we are interested in slightly more complicated one, a linear transformation of it, where we have y equals a sine of bx plus c and the whole quantity plus d. Right? How would the graph of this look like? If we learn this, we have learned a lot about just about every trigonometric function. So what I'm going to do is, instead of talking about the other trig functions like cosines, tangent, cotangent, all of that, let's first focus on one of them, especially the sine, and understand all kinds of things about it so that we can transfer all those concepts to the other trig functions. Cool? So let's get on with it now. So how do we draw? Now that we know the graph of y equals, can we draw the graph of y equals a sine of bx plus c plus d, where a, b, c, d are constants, right? Can we do that? We can. But for this, I need to digress and talk about a slightly different approach my colleague Tommy Elliott and I usually use. Check this out. This is a brand new concept. Most of you probably have never seen this one, which is if x old, y old is a point on y equals f of x, then the corresponding point x new, y new on y equals a times f of bx plus c plus d is such that x new equals x old minus c over b, and y new is a times y old plus d. So you kind of have to memorize this. I'll make sure that you understand what in the world this is talking about. I know you're going like, what? What's up with X old, Y old, man? Right? I'll explain all of that to you. Okay? Let's see. For this, okay. Should I? Yeah, maybe I'll express it this way. What this is talking about is, suppose f of x is just x squared. And can you tell me, can you pick a point on y equals x squared? 0, 0, right? The simplest one. Is 0, 0 a point on y equals x squared? Yeah, of course it is. Now, if 0, 0 is a point on y equals x squared, that is the old, x old is 0, y old is 0. What I'm asking here is, can you tell me what that same point 0, 0, where it would be located on the graph of, say, 2 times x squared plus 7? 2x squared plus 7, where would it be located there? That is the new values of x and y of that 0, 0 are x new and y new. Okay? Our objective is to find x new and y new. And what the claim over here is that those new values simply depend on these a, b, c, and d, and specifically in the following way. You already know x old, because like it is 0, 0, for instance. X old is 0. And C, okay, C and B would be known, because if I said some, they would be known. So we can calculate x new. Similarly, we would know A and D, and we also know y old. In our example, that is 0. So we can figure out y new using this simple formula. Cool? So every point on y equals f of x, every x old, y old point on y equals f of x, we can figure out where that would be x new by y new using these formulas. So we can plot all those points using x new, y new, and draw a smooth curve, and we got the new one. How simple it becomes. I'll show you all of this in detail. Okay, if you didn't understand it, don't worry too much about it. Okay, I just wanted to give you a quick proof of it. I put the proof in quotes because formal proofs are to be written in a certain way, which are kind of hard to follow. So I just wanted to give an informal proof with a lot more detail and phrased in a certain easier way to understand. Since x old y old is a point on y equals f of x, we have y old is f of x old. Is that true? Oh, by the way, this proof, if you do not understand it, totally cool. Okay, don't worry about it. It is for the sake of nerdy guys in the class. I'm trying to do it. Okay, or is that offensive to call people nerdy? Maybe not, because I consider myself a kind of nerd. Uh, anyway, so for those who are interested, I'm doing this proof. If you don't understand it, I don't care. But as long as you remember these things, we are good. If you have a point x old y old on y equals f of x, then that point must satisfy this equation. That means if we replace y with an y old and x with an x old, we must have y old equals f of x old. Straightforward. Okay, if that is the case, are you telling me that if x new, y new is a point on y equals a times f of bx plus c plus d, we must have a similar situation? What do I mean by that? Oh, we should be able to replace y with a y new and x with an x new, and this equation should be true? Yeah, it should be true. So that means y new is equal to a times f of bx new plus c plus d. All I did is went to this equation, replaced y with a y new and x with an x new. So this must be true. Okay. Somehow from these two things, we need to get x new or formulas for x new and y new. How do we accomplish this? Check this out. Does this have an f in it? And does this also have the same f in it? Is it the same f? The answer is yes, it is the same function. Okay, if that is the case, what is the argument of this function? In this case, what is the argument of the function in case 1? What argument? Yeah, argument meaning I told you just a little while ago, when I say sine of 45 degrees, 45 degrees is the argument. Sine of an argument, tangent of, in the same way, f of some quantity. That quantity is the argument. What's the argument here? X old. Right? What's the argument of f in this equation? Ooh, that's a bigger one. B times x new plus c. Okay. Now, because the function f is the same in both cases, what happens if we send the same argument in both cases? If our argument is exactly the same in both situations, what should f produce? Well, if the argument is the same, for example, argument is 2, in both cases, f of 2 must be exactly the same. If the argument is 3 here and argument is 3 here, f of 3 must be the same. We're not talking about the whole thing. We're just talking about f of that part. As long as the argument is the same to f, the output it would produce, that f would produce, would be the same. Keeping that in mind, we'll say, aha, I'm going to force the argument in both cases to be equal. So that means I'm going to make x old equal to bx new plus c, or bx new plus c equal to x old. That's what we are going to do. If we let the argument of f in 1 and 2 equal, we have x old equals bx new plus c. Cool? Wait. What's the big deal about that, man? Oh, the big deal about it is, what is that we're trying to do? We are trying to find a formula for x new. Okay. But when we find a formula for whatever it is, and that quantity should be on one side of the equal sign, and on the other side of the equal sign, we should have everything that is known. Okay? X nu is the unknown quantity. That's what we want to find. And on the right hand side, we should have all known quantities. Now, can we accomplish this? If we look at this formula here, do we know X old? Yeah. In our 0, 0, when we said X old was 0, yeah, we would know X old. Would we know B? Yes, when they say apply this linear transformation, they would have given us A, B, C, and D. So B is known. Is X nu known? No, we don't know that. That's the unknown quantity. C is also known. So that means using this formula, all we need to do is solve for X nu. How do we do that? Algebra. For example, would you agree that if I subtract a C from both sides, I would have X old minus C is equal to B times X nu? And then if I divide both sides by B, would I have just X nu on one side? That is exactly what we can do and come up with this formula. Implies X nu is X old minus C all over B. Ta-da! We got that formula. Cool? Okay, what else is left? We somehow need to figure out this formula. Y nu equals A times Y old plus D. Okay. Wait. Did we say X old? Did we set X old equal to B X nu plus C? This argument here and this argument here are both exactly the same. Okay, when the argument to f is X old, what is the output? Y old. So, would you agree that f of X old can be, and in fact, f of X old is exactly the same as f of Bx nu plus C, and therefore this f of Bx nu plus C can be replaced by Y old. Do you see that? If you see it, that's fine. If not, don't worry too much about it. If you need to pause and think about it, that's great. Y nu is therefore A times f of X old. I'm being patient here. Basically, I replace this Bx nu plus C with a X old because we said they are equal. And so we have A times f of X old. But f of X old is nothing but Y old according to 1. So I replaced f of X old with a Y old. And guess what? So that gives us the second formula. Y nu is A times Y old plus D. Can we claim that we have given a formula for Y nu? Yes. Everything on the right hand side is a known quantity. A is a known quantity, Y old is a known quantity, and D is a known quantity. So we can now confidently say, yes, we have given you a formula for Y nu. This is where it comes from. Cool. Okay, man, I don't know. You made a big deal about this. You will see how beautiful this approach is. So, how do we apply this? How does it help us? Now I can ask you a simple question. Given that pi over 6 comma 1/2 is a point on y equals sine x, find the corresponding point on y equals, 4 sine of 2x minus pi third plus 1. Many people would find that very complicated. But with our approach, that's going to be a piece of cake. Okay? Now, first things first. Is it true that pi 6th comma 1/2 is in fact a point on y equals sine x? I don't know, man. Yeah, I guess. No. Check for yourself. Can you check? Can you verify that in fact that statement is true? Pi over 6 comma 1/2 is a point on y equals sine x. How do you check that? Here, what we are saying is x is pi over 6 and y, the corresponding y, is 1/2. Is it true that sine of pi 6 is equal to 1/2? Yeah, sine of pi 6 is sine of 30 degrees, and we know sine of 30 degrees is 1/2. So, yep, this is true. Okay, so what are we left with? We need to find the corresponding point on this complicated looking thing. All right, does that look like, given x old is pi over 6, is it true? X old is pi over 6 and y old is 1/2, right? And what is a? We are trying to figure out, we are looking at this as a sine bx plus c plus d. So do a comparison with a sine bx plus c plus d. So a, would you agree, is 4? Good. What is b? B sine of bx. So b must be 2. Bx plus c. So what is c? As Elmer Fudd would say, be very, very careful. Is c pi thirds? No, c is not pi thirds. C is actually negative pi thirds, right? Because we have to compare it with bx plus c, or we can think of 2x minus pi thirds as 2x plus negative pi thirds. Then c is actually negative pi thirds. Cool? And d is 1. Are you okay with this? Cool. If you have identified all these a, b, c, d, and x old, y old, all we need to do is use our formulas. Unknowns, those are the given quantities. And the unknown quantities are x nu and y nu. And we have formulas. X nu equals x old minus c over b, and y nu equals a times y old plus d. Please memorize them, and these problems become piece of cake. Okay, so it's just a matter of plug and chug. X old, plug pi over 6 minus c minus negative pi thirds, right? Minus the quantity negative pi thirds, but subtracting a negative number is the same as adding. Oh, by the way, all over b happens to be 2, so we have a 2 in the denominator. So the top becomes pi 6 plus pi thirds, and common denominator is 6. So 6 over 6 is 1. 1 times pi is pi. 6 over 3 is 2. 2 times pi is 2 pi. So pi plus 2 pi on the top over 6. And that's going to be 3 pi over 6 all over 2. And that simplifies to pi over 4. Ta-da! Done. So x nu is pi fourths. And how about y nu? The formula is a times y old plus d. A is 4, just plug and chug. A is 4, y old is 1/2, so we have 4 times 1/2, plus d is plus 1. 4 times 1/2 is 2, 2 plus 1 is 3. We are done. So the new point is pi fourths, comma 3. So thus pi 6, comma 1/2 on y equals sine x gets transformed to pi fourths, comma 3 on y equals this big long f. What's up with f, man? Ugh. Control X, Control V, and there we go. Sorry about that, folks. I bet you guys never make any mistakes. Ta-da. Okay, 4 times sine of 2x minus pi thirds plus 1. Cool? All right. What else? Ooh. Well, absolutely fascinating. In the previous problem, we dealt with a very simple situation. And that was just, we figured out just one single point. Where does it get transformed? A single point on y equals sine x gets transformed to where on this complicated thing. One single point. That's the key. And now, in the next problem, I seem to be saying, start with the y equals sine x graph and draw the whole graph. Y equals 3 sine of 2x minus pi fourths minus 1. The whole graph. What? How can we do this? Oh, we can easily do this. How? Well, let's pick a few salient points. Are you familiar with the word salient? Salient is important. Okay, critical, important, salient, things that have prominence, some prominent points. And let's transform only those prominent points on the graph of y equals sine x. See where they go. And once we find that, we can draw the new points and then draw a curve passing through those points, and we are done. I'm going to show you that. Cool? So here is the idea. Once we learn how to transform one single point, we have learned how to transform the entire graph by picking only some important points, transforming them, and drawing a smooth curve. Right? Passing through all those points. So that's the strategy. So here, the question then becomes, what are those salient points that you're talking about, man? What are the important points on y equals sine x? I have marked them right here for you. One is 0, 0. Right? X is 0, y is 0. And the next one is pi half and 1. Pi and 0. 3 pi halves negative 1. And 2 pi 0. What are we going to do? We will just figure out where these 5 points, A, B, C, D, E, where do they go in this new graph of y equals 3 times sine of 2x minus pi fourths minus 1. Okay, let's get busy. And because there is more than one point, I'm a big believer of tables. So I'm going to create a table now. But before that, let's identify A, B, C, D. Cool? Okay. Compare this with A sine BX plus C plus D and tell me what A, B, C, D would be. A equals 3. Wonderful. B, 2. C. Don't tell me it's pi fourths. It's actually negative pi fourths, right? Good. How about D? Negative 1. Right? Cool. So A is 3, B is 2, C is negative pi fourths, D equals. Now let's construct our table. In our table, we'll have a column for X old, a column for Y old, X new, and Y new. Okay? All right. First, let's look at point A. This point. What is the X old of point A? What's its X value? 0. What is the Y old for point A? Again, 0. Right? Cool. Are we in a position to calculating what X new would be? Yeah, X new is simply X old, that is 0, minus C minus negative pi fourths all over 2. So plug and chug and simplify. If you cannot do this in your head, just grab a scratch paper and do this stuff on a scratch paper. You don't need to be macho and try to do it in your head. Okay, so this is going to be pi over 8. Similarly, y new, plug and chug, a times y old plus d would be 3 times 0 plus negative 1, or 3 times 0 minus 1 is negative 1. Guess what? The 0, 0 point is moving to pi 8's negative 1 on the new graph. Now, similarly, now let's go to b. What's the x old for b? Pi halves. What's the y old? 1. Yep, wonderful job. If that's what you said, pat yourself on the back. You are well on your way to becoming a wonderful mathematician. All right, x new. So again, plug and chug. Pi half minus negative pi fourths over 2. I did this in my head, but you don't need to. You can go to the side and do this calculation. Turns out to be 3 pi over 8. Right? And then plug 3 times 1 minus 1 equals 2. And similarly for C and D and E, cool, you get the idea. So it's okay if I went fast, right? And so we create this table. After we create the table, all we need to do is ignore everything else and focus only on x new, y new. This set of points, pi 8 comma negative 1 is 1 point. Can we plot pi 8's negative 1? Yeah, on the same graph if we wanted to. This is x equals pi 8 and negative 1 is the y value here. So our new new point a new would be over here. Cool? And 3 pi 8s comma 2. Hey, there's a 3 pi 8s and 2 way up above. So we can plot every one of those points. And once we do, we just draw a smooth curve between those points. Right? I have done that for you here. Pi 8s, negative 1. 3 pi 8s, 2. 5 pi 8s, again negative 1. 7 pi 8s, negative 4. And so on. Right? Those are the values. 7 pi 8s, negative 4. 9 pi 8s, negative 1. See? Plotted those points as A1, B1, C1. A1 corresponds to this old A. B1 corresponds to this old B, and so on. So, if the curve was a sine curve, the original one, this would also be a sine curve, so it would retain some of those same characteristics. Okay, so we just simply draw another sine curve, but making sure that it passes through these points. So we have drawn this, what is supposedly a very complicated one. Okay, now the truth is, what we have drawn is only one single period. It is not true that the original sin x graph is only this part. It's a periodic function. It just keeps on going. The same pattern continues on, right? Whoops. The same pattern continues on. In the same way, our new graph, even though what we have shown is just for one period, the truth is this could be extended and should be extended to go like this, and the pattern keep repeating. From here it keeps going up and hits that same peak of 2 and comes down, and the pattern repeats. Or in other words, take this entire graph and scoot it over so that A1 falls on E1, and you get You get all of this repeating over here. And again, place it over there, and that repeats, and you can keep doing this. That's the actual graph. All right. Boy, we went through quite a few concepts, right? Allow me to mention one more concept here, please. Back in school, quite possibly your teachers talked about, well, boys and girls, when we multiply by 3, what happens? That stretches the graph. And what about this -1? That shifts the graph down by 1. Horizontal stretch, horizontal shift, the vertical stretch, vertical shift, and all that. We will talk about that. That is important to know. But the main point I'm trying to drive at is, we really didn't have to learn all of that. We didn't have to say, sine, because we have sine of 2x, that means this is shrunk in the horizontal direction by twice the amount, and because we have a negative pi4, this is shifted to the right by some amount. We don't have to do any of that, right? We can still plot the point accurately, plot the graph accurately. That's the key. But we will talk about what is the impact of each one of those parameters, A, B, C, and D. Cool. Do I have something else? Yeah, let's look at one more graph. Draw y equals -2 sine of 3x plus pi half plus 1. Okay, the process is exactly the same. A is -2, B is +3, C is pi half, D is 1. Would you agree? Cool? Yes, good. Now, what is it that we do? Again, make a table like this. I'm not going to go over everything, but what is key is the x old, y old are always more or less the same. Those that correspond to y equals sine x graph. On y equals sine x, we have a 0, 0, pi half 1, pi 0, and so on. So that part remains the same. And they are still A, B, C, D, E. The only things that change are the x new and y new, because A, B, C, D have changed. And so calculate all of these things. Pay attention to this. There's one thing that I definitely would like to point out. So the first x new turned out to be -pi/6, and this one turned out to be 0, pi/6. But when we calculate this, we get pi/3. On purpose, what I have done is, recognizing that this is pi/6, in the denominator we have a 6, on purpose converted this so that its denominator will also be equal to 6. So how do we do that? If the denominator is 3, we want to make it a 6, well, multiply that by 2, right? But you cannot just multiply the denominator alone by 2. As long as you multiply the top also by 2, you are okay. So multiply both the top and the bottom by 2, making it 2 pi/6. Pi/3 is in fact equal to 2 pi/6. Similarly, we have pi/2, but we want the denominator to be 6. So let's multiply both the top and the bottom by 3, making it 3 pi/6. The reason we do this is now we can figure out that every horizontal grid line must be pi/6 distance apart. What? Every horizontal grid line should be pi/6 apart. Let me show you that. Check this out. So on a graph paper, you pick a grid line and say, well, the smallest value is -pi/6. So one grid line is -pi/6. And then 0, of course. and this is a pi over 6, 2 pi over 6, 3 pi over 6. So each grid is pi sixths apart, right? And once we do that, we again create horizontal ones in order to plot the y values, these horizontal lines. And this is -1, space them equally. 1, each grid is vertically is just 1 unit apart. And so do this 1, 0, -1, -2, -3, and so on. Well, sure enough, we have a point called -pi6, -1. That's what we have here. So just first plot the points. Sorry. First make the suitable grid. Okay, both the ticks, these are called tick marks. Make it ticks on the in the x direction and ticks in the y direction. Space them equally and be guided by this common denominator thing, pi over 6, pi over 6, pi over 6, multiples of pi over 6. So you make it this way, and that allows us to plot the points effortlessly. The next order of business is to plotting these 5 points. So -pi over 6, -1, ta-da, that's where it's located. 0, -3, located here. Pi over 6, -1, over here, there. And once we got this, guess what? We draw a smooth curve from A1 to B1, B1 to C1, C1 to D1, D1 to E1. A nice smooth curve, right? If need be, you can extend this graph. But drawing this shifted graph for one period is typically good enough. Cool? Did that make sense, folks? Okay. All right. I think that's a good place to take a pause. There are a few more things that we need to cover, but I think that's a good stopping point for today. Okay. I'll make a part 2 of this and cover all that other stuff. Alrighty.